Do you have anything to ask?
I think, is this I heard it.
He's coming from Seattle University and presents something somewhat more at larger scale than what we were used to in these days.
Okay, thank you. Great. So yes, I'm going to step back much farther away from the detail, grain by grain processes that we've been talking about so far. And when I was asked to give the talk, I think Enrique and Astrid titled it Channel Floodplain Complexes. And Bill, Dietrich, and I spoke about this a little bit. Bill's going to give a talk after mine. We'll cover even larger scale and lower slope systems than what I'll be talking about. We were wondering what complexes meant. And I've shown a photograph here that illustrates what I think a channel floodplain complex is. It's not just a channel or just a floodplain. It's actually got a bar. It's got multiple sediment sizes on the bar. You can have gravel and sand in both places, at least on this system. This happens to be in Nevada. It's the Walker River that drains the eastern Sierra Nevada range. And there's also gravel and fine material in the floodplain. Okay? So there are various ways to entrain that material in the channel. And I think the rates at which that occur are important. So my talk is going to focus primarily on a few case studies. I'd like to, and before I do that, I'd like to thank a really large number of people who have helped on this work over the years. I'll be summarizing projects that have happened over the past 6 or 7 years, maybe further back than that. Many of the ideas at least the modeling ideas, originated with Gary Parker. So he's at the front, but there are a large number of other people there. Okay, and so I'd like to start, now I'm going to move to a somewhat different system. The photograph that you see here is an aerial photograph of a river close to my home in Seattle. It's actually an engineering project that I was working on with some students. That's why there are levees shown on the photograph. Those levees were constructed to redirect flow under a bridge. It's a pretty standard engineering project. But they eroded. And so the county was interested in what had caused that. And you can go out and do some sediment transport calculations in that channel. This bar that formed is pretty big. But it's of similar magnitude to maybe an annual sediment transport capacity. I mean, plus minus 100, 200%. But the overall sediment transport capacity in a system like this is not dramatically larger than some of the large-scale bars that you can see that appear to be interacting with the flow, and thus perhaps, if you like the idea of bar push, orienting flow into the bank and then causing additional erosion, which allows additional sediment to then move downstream. Okay, so that's the answer to that first question. Why consider floodplains? Well, I think they are an important source and sink for sediment. And I'm going to go through this using 3 case studies that incorporate both numerical modeling in a very simplified way and some field data. So all of these cases are sort of intended to illustrate why floodplains might be important. I'm not trying to show that we have the best model for representing all processes. So we'll start with the Walker River in Nevada, which was that first river that I showed on the title slide. And a really simple model, I'll call it a toy model, for how channel floodplain exchange might work. We'll move then to a somewhat more complex model motivated by the Minnesota River, which is a larger river, sand bed rather than gravel bed. And then we'll finally end up again in Washington State on the Elbow River, which is the site of several large dam removal projects that have been completed in the past several years. So there's a very large pulse of sediment moving downstream. I'm not going to spend a lot of time talking about the effects of that pulse of sediment, but I'd like to use that as a case to illustrate a model for channel floodplain exchange. And then I'd like to end by talking about research needs. Okay, so the first and simplest model for channel floodplain exchange, I think, is one where the channel erodes one bank and a similar amount of material ends up on the other bank in a bar. So it may not be the same bar, it may be the next bar downstream or several bars downstream. But if the channel is migrating, this is a stratigraphy that I've seen represented in many papers. So let's work with it. Let's go with this idea. If you had a channel that's migrating eroding material from one bank, depositing it on another bank. Well, there's probably some fine material here that doesn't end up deposited in that bank right away. This is an example from the field of the same kind of picture. Here we have fines up above, maybe gravel and cobble at the toe of the cut bank, and then you have gravel and cobble at the toe of the bar bank on the opposite side. Okay? You don't see the fines, at least immediately, but if you give it enough time, presumably those fines will accumulate. So it may take years. Some of them may come in quickly. But as the channel migrates away from that point, before the channel finally migrates back to that location, you should have accumulated a pretty nice package of fine sediment on top. Okay? So, in principle, a river could be in a rough dynamic equilibrium where on average, the gravel eroded is similar to the gravel deposited in banks. So bar material, maybe we shouldn't call it bed material, but the amount of bar material eroded could be similar to the amount of bar material deposited. And then over a long enough time, the fine material eroded from the cut banks could be similar to the amount of material that accumulates over bank. And you can actually calculate exchange distances if you make this assumption that everything's in equilibrium. So if we have a sediment, it's interesting to compare these to the overall down-channel sediment load in these systems. I'll do that on the next slide. Just one other point here. This is a figure from a paper Gary and I worked on in 2008 when we were looking at the direction that these channels tend to migrate. This shows a plot of the rightward migration rate in the dots, and then the blue and the red are the bank elevations. So if it's moving towards, if it's positive, if this is a positive number, it's migrating towards the red line. Okay? So in this case, high number of rightward migration. It turns out the rightward bank, the right side bank is high. Same here, same here. If it's migrating to the left bank tends to be higher. Okay? So this overall accumulation of fine material is one way that you can explain that. I'll talk about a few other possible explanations later on. Okay? All right, so we could try to estimate the overall fluxes, in fact, by looking at how rapidly it's migrating into a bank. We can get the amount of material eroded from these banks as long as we know the size of the bank and the rate at which the channel is migrating, which could be measured from aerial photographs. So I've done that in the case of silt and sand. So we had a series of systems that had sandy bars and then fine silt or clay packed on, deposited on top. And we compared that to the overall load. If you just look at the exchange flux, the migration rate times the thickness that you're eroding into, porosity factor, and then times a spatial parameter, you can get an overall flux. We can compare that to the down-channel flux and then calculate an exchange distance. Actually, this should be the flux per, sorry, the Q exchange should be a flux per unit length. It shouldn't have the delta X in it. You can solve for delta X from that. Okay? So it gives you an idea sort of a characteristic exchange length. I think Rob Ferguson spoke about that earlier. For fine-grained material, not pretty long. It takes a long time to exchange that much material. But once you get down to the size of bar material, in sandbed systems, you're talking about kilometers over which you would exchange that material, given the measurements of migration that we have. And similar work has been done by Christian Broderick. Bill Dietrich provided this photograph or image for me the other day. Same basic calculation where you're looking at the coarser fraction in gravel bed meandering streams. It's actually harder than you think to come up with the numbers required for doing these calculations. Especially with the case of gravel bed rivers, tend to be maybe on the smaller sizes of the overall meandering river spectrum. So measuring migration rates is sometimes challenging. And in addition, knowing how much gravel is actually in the bank can also be challenging. So there are some assumptions that go into that. In fact, these numbers for down-channel load, the overall load, were calculated from a transport equation. So I don't know how accurate they are. They probably lead to scatter. But for the most part, you're getting numbers that are on the order of, and this is like this in terms of bins, you're getting numbers that are just on the order of an individual bin or less. Right? So the gravel doesn't move very far once it's in train. Okay? So that's the simple model. I think as you get coarser, the sediment particles probably tend to move shorter distances. Okay, that assumed an even exchange. But what if it's not? Okay, so there are several ways that this exchange may not be even. The first is illustrated here. I'm going back to this river in Nevada, Walker River. It's a desert stream, agricultural area. Gravel bars, Peter Wilcock lying down taking a nap on the bar gives you a sense of scale. And then similar size gravel in the toe of many of the cut banks, but not all of them. And if you remember that first photograph, there were fines packed all the way down to the toe in some places, and other places there are channel deposits, right? So it's complex, is the name. Oops, sorry. So what we tried to do here was see, well, really, how even would this be? How even is the exchange? Are getting similar amounts of gravel eroded as deposited? And it's kind of hard to do that calculation, and I hope I won't convince you that we did this right, because I'm sure we did not. There are large error bars on all of these numbers. But what we tried to do is estimate in all of the cut banks a typical thickness for gravel, for sand, and for silt. We did that every 20 paces over many bins. We came up with about 100 profiles, and then did sieving to characterize the size distribution for each. And we came up with roughly 40% gravel, 30% sand, quite a bit of silt and clay, for a total thickness of about 1.2 meters for most of those cut banks. Okay? But the total of the gravel was probably about 40 centimeters across those banks. Okay? So what I'd like to do, we don't have great down channel sediment load estimates, but let's see if we can come up with a model where, or what would it take to have a model where you actually have bars that are higher than the amount of gravel that's being, the typical thickness of gravel being entrained from cut banks. So we'll try to look at this, we'll look at a net storage and see how that would compare to the down channel flux. So first of all, you can measure lateral change. It's harder than you might think because this is a pretty small river and the air photos aren't perfect and you don't align them perfectly. If you just lined up one air photo with the next, look at the area of banks that had eroded, you get about 60 centimeters a year. That may be too high because of error. So there are other ways that you can do that. One that I like and played around with the other day, Constantine et al. In Nature Geoscience relate sediment transport rates to channel migration rates. And within their paper, they actually look at the rate at which oxbow lakes form. Oxbow lakes form because the channel migrates and sinuosity increases. And so given their overall relationship between oxbow lake formation and channel migration rates normalized by channel width, you can back out a relation that gives you a migration rate as a function of the elongation rate of the center line. And on this system, we actually did have measurements of the center line elongation rate. We had no cutoffs, but we still could back out a migration rate. So probably lower than what we got from the air photos, but still, tens of centimeters per year. And I'm pretty confident that that's the case. All right, point bars. So we needed to know the size distribution and thickness of the point bars. We did some sieving of the subsurface. The gravel was easy enough to pull off. So once we had the subsurface, 50% sand, 50% gravel, plus minus who knows how much. But there's, order of magnitude, maybe 50 centimeters worth of gravel in those bar deposits. Okay? Cut banks, again, I said maybe 40 centimeters of gravel. So there's a difference. We don't have a lot of data. I'm not confident in that difference, but there's a good chance that there's a difference between the thickness of sand and the thickness of gravel on cut bank side and thickness of gravel on point bar side. So how does that compare to the load? Well, there were some bed load samples that have been taken. They there was a study done for one water year where they looked at gravel, 7 or 8 bed load transport measurements, developed a rating curve, come up with a pretty low sediment transport rate. And so if you divide the transport rate by the exchange rate, you only get 5.5 kilometers. That's given only a 10 centimeter thick difference between the thickness of gravel on one side and the thickness of gravel on the other. Something that's really hard to measure, but it can account for all of the sediment load in just 5.5 kilometers, right? And you actually see a lot of downstream lining on the system, okay? And the curvature of the profile, we are coming off of an alluvial fan here. There's a little bit of curvature over the first 2 points, maybe here, but between kilometer 45 and 55, there's virtually no curvature in the profile at all. You can explain the capture of the gravel looking just by the difference in thickness of gravel on one side and the other side of the river. Okay? All right, so I think this dynamic, this exchange with the floodplain can have pretty significant impact on bed material transport rates. this idea has been around in other contexts for a while. There's this idea that in the eastern United States, there are legacy sediment deposits. Floodplains accumulated a lot of fine material during the early agricultural period. And that material is now slowly being reworked by rivers. And in fact, there's a paper that just came out in geomorphology last year looking at that size-specific exchange. Well, at least they talk about the possibility of size-specific exchange, where you erode fine material but replace it with coarse. So very much like what I had just argued could be the case in the Walker River. Okay, so this would really explain, I mean, you could not explain bed material transport rates without accounting for this process. And they looked at overall erosion, overall deposition, really roughly similar numbers. And there's a net difference that's a pretty small number in between those. But there's a pretty good chance that there's a pretty significant size fractionation, a size-specific storage that's going on as part of that process. Okay, so here's the toy model. Let's forget about the fines right now, and let's just consider a river that has gravel on one side, gravel on the other side, and then it's got a bed that also has gravel. And let's keep it super simple now. I know this is a sorting conference, but let's just use one sediment size. Let's see if we could, we'll have a cross-section that looks like this. Channel zone here, and then we have this, you can call it a terrace if you want, off to the side, and probably on both sides of the channel, but just think of it as an off-channel storage reservoir. If the channel's eroding into the terrace, it's getting material from that terrace. And it's going to be replacing, moving material back out at some other rate, some thickness that's probably specified by the hydrology of the system. It's high, it can build gravel bars up to a certain height. And there's several papers out there that would indicate on some systems or in some scale models, again, citing Christian Broderick and some of his experiments, typical meandering migration would produce a typical point bar height. Also on the Fraser River, typical bars all roughly a certain constant distance above the gallway. So that's the model here. We're assuming it moves out at a constant thickness, but it comes in at the average thickness of the gravel deposit, which may be more or less than the gravel bar thickness. Okay? So we have one model for the thickness of that terrace, or one equation for the thickness of the terrace, T. And then there's another equation for the bed elevation. Okay, so pretty standard Exner equation here, but it includes this lateral exchange term. Migration times the terrace thickness per unit width. And then, again, this is just the overall mass conservation for the terrace box. Okay, and the box will rise or fall as a function of imbalances in this exchange source. And then just a Meyer-Peter-Mueller, Wong and Parker equation here for down-channel sediment flux. So these are what the simulation gives you if you imbalance, if you create an imbalance in the sediment supply. Okay, so we started from a graded case where lateral exchange out and in the lateral supply in was equal to what was being deposited out, and then we cut that, we cut the down-channel flux by, I think, a factor of 2 on these runs. It's driven by a full flow duration distribution. Sometimes flow can be up above the top of the terrace average elevation. Sometimes the flow is below that elevation. So you get a down channel capacity based on this flow that you calculate in the channel. That's how you calculate the transport rate. And let's see if this stopped. Let me start that again. Sorry. So this is the case where it's degrading. You might look closely, the red line actually falls faster than the blue line for a while. It's sort of incising, but the bank becomes thicker as that happens, and so the terrace supply becomes larger. That would sort of be like this, where you actually have gravel that's thicker than the bar that you would be depositing, and that moderates the incision so that eventually you stabilize at a new level where now you're just at grade. And then
what's the blue and red line again?
So blue line is the top of bank. It's the terrace elevation. The red line is the bed elevation.
Okay.
Okay. So same, and then over here in the case of the increasing the load, now we have a bar thickness that's higher than the average terrace. So there's a net supply. Sorry, there's actually a net imbalance that causes the bed to grade because of that exchange process. Eventually it gets to a new grade. Okay? So that's the idea. It's a pretty simple idea, but the point is that a small imbalance in these two lateral fluxes could impact the bed. Okay? So that didn't have any fines, but I started the talk by saying there are also fines in floodplains. So how would you incorporate fines into such a model? I'll use the Minnesota River as a way of illustrating this concept. This is a modeling project on the Minnesota River, and then prior to that we had done some work on the Lauer River, which is a tributary of the Minnesota, sediment budgeting work that ultimately generated this model. So it's a sandbed river, it's got fine floodplains. The model, and I have to thank Enrica Viparelli and Gary here, both for a lot of contributions on this work, is now a little bit more complex than the toy model. So instead of having just a terrace and a bed, it also now has a substrate, and the